Hey, I'm Scott. I'm going to talk to you today about ELSSIE. So one of the challenges of sampling Europa is using the Europa lander cameras to find the spot on the surface nearby the lander that contains evidence of habitability of the ocean and potentially biosignatures to measure from somewhere within a 2 square meter workspace, and do this in just a couple of days within the confines of a 22-day mission. Now, this sounds extremely challenging, and it will be, but we've actually done something related before, and that is finding the Mars 2020 landing site, granted at a much slower pace, but with a similar objective of using a spectral signature of a mineral to find a past habitable environment that has the potential to preserve biosignatures. So we can take a lesson from how that was done using data from the CRISM and other instruments on MRO looking for carbonates or other minerals that would evidence potential landing sites and materials to sample. This is actually the discovery image in which carbonates were first identified on Mars. And you see a 3-color composite here from visible wavelengths. From these data, you can guess at the presence and location of carbonates or other minerals of interest from color and morphology, but you can't be sure because the diagnostic features are in the infrared. This is the infrared part of the same image using false color, and here you can directly detect primary mafic minerals, clays, and carbonates because they have strong spectral signatures at these wavelengths. And to give you the answer, the inset at the right here, that bright green material, that's the carbonate. You just can't see it at the visible wavelengths. Now, the attributes that make a material desirable to measure in situ also will address the other science goals of Europa lander. For example, one of the indicators of an interesting material will be concentrated salts, showing that you've got ocean water. That salt chemistry also illuminates the chemistry of the ocean and its potential habitability, and the spectral signatures to look for are 1.3 to 2.6 microns. The ideal material to sample has the least radiation damage of the material at the site, leaving complex organic molecules intact. And this signature of that could be fresh amorphous ice or ice that has crystallized, but not older ice whose outer rims have been damaged by radiation. Finding this desirable material also is an indication of geologically young ice emplacement, and the spectral signatures of the interior and the rims of the grains would be at 1.65 and 3.1 microns. Finally, organic compounds would be the indication of a potential biotic material, and those are evident from absorption features at 3.2 to 3.4 microns. Now, I will try to convince you that the Europa lander should be surveying its landing site and its workspace in the infrared. This iconic Galileo false color visible image shows Europa at 1.6 kilometers per pixel, and this clearly a spectrally heterogeneous surface. Let's zoom down to just the 3-pixel scale in this image, and you've got the highest resolution Galileo image that you've taken, and what you see is the heterogeneity extends down to the smallest resolvable scales, and the contrasts are even larger. If we zoom down to 1 pixel in this image, that's the Europa lander's landing site and the workspaces within that. It may very well present a variety of materials. However, IR spectral variations are only known at very low resolution, not like the visible resolution you see here, and the use of visible color as a proxy to find them is really unknown. So ELSSIE addresses these issues by taking landed imaging into the infrared. It actually has 3 sensors. There are dual stereo imagers, a right eye that covers 0.4 to 1.8 microns, and a left eye that covers 0.8 to 3.6 microns. Each eye has a 15-degree field of view and 375 microradian pixels. 20 spectral filters between the 2 eyes are in 4 groups. One group matches the spectral filters on the ICE imaging system on Europa Clipper to extrapolate color variations you see from orbit to the landing site. A second group discriminates ices and hydrated salts. A third distinguishes crystalline and amorphous ice at both the scales of the grain rims and the grain interiors. And a fourth group of filters detects organic materials. The third sensor is a point spectrometer with a 2 milliradian field of view that samples the surface at better than 10 nanometers per channel, and that will characterize any heterogeneities that you identify in the images at much higher spectral resolution, allowing you to identify a range of minerals and organic compounds. This CAD rendering of the exterior of the instrument concept shows the outer surface that acts as a radiator to passively cool the optics in the focal plane using the surroundings to a working temperature of 115 Kelvin. And you can note the Cyclops design where the two eyes are the stereo imagers and then the little eye in the middle of the forehead is the point spectrometer. If you take away the housing, you can see the innards of the instrument, and fold mirrors bend the field of view of both cameras through a pair of miniaturized filter wheels on both eyes, and mirrors reflect the light onto different parts of a single detector that is shielded by a radiation shield to minimize the noise from the radiation. And the point spectrometer folds its light around the radiation shield and uses another unused part of the same focal plane array. Here's the optical design of the two eyes. They're subtly different because of the different materials and wavelength ranges, but each eye has an adjustable focus, so you can focus nearer or further. And on board, a technique called Z-stacking is performed to create a best focused merged image. This shows a flattened version of the optical design of the spectrometer. It uses what's called an Offner design and a small Cassegrain telescope. And note these little light bulb icons. A field-filling optic in all three sensors has a rear surface that is partially silvered and will diffusely transmit light from a closed-loop control calibration source, enabling a landed radiometric calibration to be done on the data that are collected. Here's the block diagram of the instrument. The sensor containing all three sensors is located on the high gain antenna. There's motors to control the filter wheels in each eye as well as the adjustable focus. And then the data processing unit is located in the lander's radiation vault. There are 3 cards. A digital card contains processors and memory to process data on board to squeeze down the data volume. An interface card communicates with the spacecraft and also drives the motors, the calibration lamps, and a heater. And the third card provides power to everything else. So this graph shows how the spectrometer will detect different materials on the surface. You see here in yellow and light blue, Europa icy and non-ice materials, and in green and orange, mineral analogs to the non-ice materials. The black lines are simulated spectra as sampled through the point spectrometer, so they're nearly laboratory quality. And the region of interest is here around 1.4 to 1.5 microns. And this shows the same data resampled into the band passes of the cameras. The minimum reflectance in ice is at 1 wavelength, and the minimum reflectance in hydrated salts is at a different filter. So it's easy to distinguish concentrated salts from the background ice. And in addition, there's a filter at 1.25 microns that measures the depth of a band that's very sensitive to ice grain size, allowing one to map out differences in surface texture at the landing site. This is a 2.8 to 3.6 micron region. Again, Europa materials on the bottom plot, aromatic and aliphatic organics in pink and green, primitive meteoritic material that contains both in black, and in the bottom, crystalline ice. Note the ice that is fully crystalline has this pronounced reflectance peak at 3.1 microns that's lacking in highly radiation damaged ice. These are the right graph is those data resampled into the camera band passes, which could easily distinguish concentrations of organic material as well as occurrence of crystalline ice. Now, the data processing unit is essential to the operation of the instrument. It mitigates the radiation noise in the data and helps to control the data volume. The mitigation of the radiation noise uses a technique that's been developed for the MISE imager on Europa Clipper. For every frame position, there's actually multiple integrations. You throw out a subset of the highest values, which have the radiation noise, and you co-add the rest to improve signal to noise. To squeeze down the data volume, for 16 of the 20 filters, we use a technique that we pioneered on CRISM called summary products, where you take many wavelengths of light and reduce them down to a few parameterized variables that show spectral variations. These will be created on board by calibrating the images using the calibration data that you've taken, rescaling the pixel scale of each image to the common stereo filter to both eyes, and then performing band math, compressing and downlinking the summary products. The calibrated data will reside on board, and from the ground can be interrogated for the 20-channel spectra to provide more detail on whatever of interest shows up in the summary products, and the spectrometer can target regions of interest for further information. ELSSIE is fully capable of addressing Europa landers' science questions about habitability and geology, including exogenic and endogenic materials deposited on the surface, tectonic features on the surface, and radiation processing, using a series of 8 different imaging campaigns, including stereo and change detection mosaics of the landing site, spectral images of the workspace, and at different nested resolutions and higher quality spectral information, coverage of the trench as it's dug and the sites of the samples that are collected. So in summary, ELSSIE merges the traditional capabilities of a landed imaging system, high-resolution stereo, change detection, and color mapping, with new capabilities that are enabled by its coverage in the shortwave infrared, mapping of compositions, detection and discriminating minerals from ice in the background, detecting organics, and determining variations in ice crystallinity that point you towards the freshest material to collect for onboard analysis. Thank you, and I'm happy to take any questions.
Do we have any questions for Scott?
I missed why the mission is so short. Is it the radiation damage?
Yeah, the radiation damage for the spacecraft. So what that does is, most of your mission, you want to be harvesting samples and analyzing them on board. So it puts the onus on the context cameras to find that spot fast. And that's why the onboard spectral capabilities and onboard processing minimizes the back and forth between the ground and the spacecraft to do that while you've got still 3 weeks of lander life.
Why is it only 3 weeks?
Because the radiation, as explained by Cynthia in the previous presentation, because the radiation will kill the lander in about a month.
Well, then it could survive for up to 3 months, which is about the radiation lifetime of the lander. But in terms of getting through the baseline mission of 3 samples, we can do that in 7 days. Then there's an additional 7 days of margin and an additional 7 days on top of that, which puts you at the 22 days, which is also a multiple of 3.55 days, which is Europa's diurnal cycle around Jupiter. So the 22 days is our nominal mission with plenty of margin, but then using up our mass margin and allocating that to primary batteries leads to an 80-plus day lifetime.
Excellent. Thank you.